That was a Matlab simulation of the 8-bar vector loop analysis that we just did in the previous videos. And this video is going to show how to actually make that simulation in Matlab. So we'll figure out how to take this vector loop math, put it into Matlab code, and then run in a simulation that includes the animation of the moving linkage and also static plots of the unknowns versus the input for position and velocity. So let's get started with Matlab. So open up Matlab, and then you want to make a new script. So we'll first go into a folder. So I made a folder called 8-bar example. That's where we'll put this code. So the first thing we want to do is put an outline of comments. So the very first thing we want to do in the code is clearing out any old junk. So that would be using the clear command, which wipes out the workspace here. Then close, which would close any figures that are already open. And then finally CLC, which clears the command window. So after that, then the first thing we need to do is define our knowns. Then after that, we'll define the inputs. And then pre-allocate arrays for the unknowns. Define our initial guesses. Solve the loops. So in order to solve the loops, then this would be using Newton's method. For anything that involves multiple vector loops, Newton's method is usually the easiest route. It's very difficult to solve algebraically. And like you saw in the previous videos, the math that we did is pretty much impossible to solve it by hand. So that will include a for loop. So for every value of the input, and we will define in and all that other stuff, but basically we want a for loop there. And then inside the for loop, we will need to determine position error, which will be the position scalar equations. Then while the error is greater than the tolerance, we need to solve the while loop with guessing and checking. So that will include a while loop while the error is greater than some tolerance, which we will define. Inside of the while loop, while the error is greater than a tolerance, then we will need to determine the Jacobian. Do our guess and check with updating guesses. And then again, we'll need to determine the position error to know if we have solved correctly or not. So then finally, once we have found the correct answers inside of the for loop, but outside of the while loop, we will save the correct answers. And then we will calculate velocity. So we got position, we got velocity. Once we have found the velocities, then we'll need to calculate the points to plot and then put those into lines and then actually make the plot. So that's how we'll solve for the animated part. Then later on, we will get the static plots. but let's do this first. So now that we have figured out our outline with comments, we're going to fill in the math. But first, let's save our code. So we'll save as, and then we can call this 8-bar loop, vector loop simulation, or pretty much whatever we want, but we need to actually type the word 8 out. We can't use a number 8 because Matlab cannot understand a file that starts with a number. So you can put the number in there somewhere if you want, but it can't be the first letter. Now we need to define our knowns, inputs, all of this stuff. So let's go back and look at the math. So here I have just pulled over all of the equations that we're actually going to need for the programming part. So just to look back at the vector loop, you can see that we have the bottom loop in blue, the right loop in red, and the left loop in green. And then we have our knowns, unknowns, and input all laid out at the top, and our constraint, theta 6 equals theta 5 plus gamma, which is for the triangular link. So then underneath that, we've got the position scalar equations, and then we've got the velocity in matrix form. So the first thing we need to do is figure out some actual numbers for the knowns. Now, the easiest way to do this is just to draw it or print it out and get out your protractor and your ruler and measure it. So that is actually what I did for this. And then I got centimeter and angle values for all of these measurements. And that also will help with the initial guesses because you want an initial guess that's close to the true value. Okay, so now we have the vector loop diagram and the knowns, unknowns, inputs, constraint here to look at while we type these in. So the way to get the knowns or the constants is basically just to measure directly onto the picture because you want to make sure that these come out to something reasonable. So when you put in all of the measurements, your vector loop should be reasonably close to a 0 value. So just typing these out, I printed this out on paper and then used a ruler in centimeters. So all of these units are going to be in centimeters. So I got R1 equals 6.2, R2 equals 0.85, R3 equals 4.8, R4 equals 3.2, R5 equals 3.3, R6 equals 2.5, R7 equals 2.6, R8 equals 4.5, R9 equals 5.8, R11 equals 6.8, and R12 equals 2.1. Now we didn't have an R10 because remember R10 is one of the unknowns. So we just went through these lists of the known link lengths. So next we have the angles. So a lot of these angles we can just look at and know, like R12 or theta 12 is at 0 degrees, theta 9, theta 11 are at 90 degrees. But gamma we would actually have to measure. We do need to know gamma because here it's in the constraint and it's not going to change. So that one we have to actually measure. And then theta 10 we would also have to actually measure and then put these into radians. So let's see. Theta 12 equals 0 degrees. Theta 11 equals 90 degrees, which is pi over 2. Theta 9 equals pi over 2 also. Gamma equals 60 degrees, so that's pi over 3. And then theta 10 equals 5 pi over 6 plus 0.1. So 5 pi over 6, that should be. So basically it's not completely pi, as you can see here, it's not exactly to 180, but it's almost there. So it's basically 180 degrees minus a little bit. So that's how I got this one. So next we need to define the input. So we'll need to know, as we have down here for count equals 1 to n on line 34, how many different degrees do we want the input to go through, or how many different positions do we want to show it at? So the more points you have, or the higher the n value is, then the smoother your plot will be, but also the longer it will take to animate. So generally somewhere between, like, depends on your range of motion, but like somewhere between maybe 20 and 100 is good. So let's start with n equals 20, because that'll be the fastest to calculate, and then we can ramp that up if we need to. So we'll say n equals 20, and then we need our tolerance value. Our tolerance is basically how close to 0 do the vector loops need to be. The more vector loops you have, the bigger you can make the tolerance, because the individual loop error would still be small. But generally something at like 10 to the minus 2, 10 to the minus 3, even up to 10 to the minus 6 would be fine. So again, a tighter tolerance will make it take longer to calculate, but it will make things also smoother and a little bit more accurate. So let's start with tolerance equals 0.001. So if we had in centimeters, then 0.001 would actually be 1/10 of a millimeter. So that's kind of small. Let's just, yeah, so 0.01 1/10 of a millimeter accuracy is probably close enough. So we'll go with that. Next, we need our actual inputs, which would be theta2. So over here, we have the omega going there. Theta2 is the input, and we need to figure out its starting and ending position. Let's have it start over on the right side and end over on the left side. It won't be able to make a full circle or one complete revolution, just because basically the linkage would get stuck. Like R7, R5, R3 would all be lined up straight. R2 still wouldn't be able to go in a full circle. So let's say that theta2 start is maybe negative 30 degrees. So it would start kind of pointing down like this. And then theta2 end is going to be a little bit more than 90. So it will point out a little bit kind of to the left of R9. Now we need to also figure out, we'll use a linspace command to set a range from the start to the end. So Q2 equals linspace, which is linearly spaced vector from the start to the ends and number of points. And then finally, we need the velocity. So we'll just say Q2 dot, we'll just call it Q2D equals 1. So velocity can be anything. It's easiest to make it a constant value. So we'll just put it right there as a 1, and 1 is just an easy number. Basically, don't make it 0 or all your velocities will come out to be 0, and that won't make sense if you're trying to animate something. But this would be in radians per second, just, you know, whatever speed you want R2 to rotate at. So then pre-allocating arrays. Now we'll need to pre-allocate an array for all of the unknown angles, and then again, all of the unknown velocities. So pre-allocating the arrays has been covered in previous videos, but this is to help set up an empty matrix that you will be filling in as you calculate the unknowns for each position of the input. So we'll just make an empty vector, and that will be zeros of n rows, 1 column. And now we need to pre-allocate an array for everything we would calculate. So we'll say that all of our unknowns start with theta3, Q3 equals empty vec. And so on, we're going to do this for all of them. Q4 equals empty vec, basically just setting up an empty vector for everything. So now we need to define the initial guesses. That will be the first element, or the starting position, for everything in all of our unknowns. The way that the linkage is shown is not exactly in the starting position, but it is going to be pretty close. R2 will start over on the right, below down a little bit. So you can get your initial guesses by measuring off of the graph, or you can just guess, but you want to at least get them in the right quadrant. Okay, so looking at this picture, we can pretty much get our unknown angles in the right quadrant. Unknown lengths, like, so guessing for R10, that's going to be the hardest one to do, but you just want to get things pretty close, and then Matlab will be able to figure out the rest of it. So for our initial guesses, theta 3 looks like it's about 30 degrees. So we'll say Q3 of 1, because that's the first element is going to be the initial guess, equals 30 times pi over 180. And then theta 4, that looks like maybe 120 degrees. Q4 equals 120 times pi over 180. And then theta 5, that looks pretty close to 30 again. Theta 7, so we need to put the parentheses 1 and all of these because it is the first element. We don't want to overwrite the whole array that we pre-allocated. Okay, so theta 7, that is pretty steep, so, but it's still less than 90, so we'll say 80 times pi over 180. And then theta 8, that is pretty close to 180, but not quite. Slanted up a little bit, so we'll say pi minus 0.1. And then we'll have finally R10, and we will just, for R10, we're just going to estimate from the plot, so that will be about 0.6. And that is in centimeters. Okay, so now that we have all these initial guesses, we need to put them in a guess matrix. So let's make a matrix and put out, we'll just stack all of these unknowns in it. So we're going to list out all these unknowns and we'll put them in a column matrix because that is how we will need them when we multiply in our while loop. So we'll just call it G for guess equals, and then we need to stack all of these unknowns. So we'll start with Q3 of 1, and then Q4 of 1, basically starting with the thetas and then going in increasing order of subscript, and then we'll do the R's next. So then we'll solve the loops. So for count equals 1 to n, we actually need to figure out the position error because we want the vector loops to equal 0. Let's look at our vector loops. Okay, so we have these position scalars. We want each of those to equal 0, but because we have actually guessed for the unknowns, those loops are probably not going to equal 0 unless our guess is spot on. So we need to calculate what is our error. So we will type out each of these and we'll say xb for blue equals negative R1 plus R2 times cosine Q2 of count. And remember, anything that changes, you need to index using that parentheses count. Plus R3 times cosine of G of 1. And that's because we guessed on R3. So we're going to use the R3 that came from the guess matrix. And then minus R4 times cosine of G of 2, second element of the guess matrix. And then YB, similar. So we have all of these position equations here, and notice that for the R6, I used G3 plus gamma, so third element of guess, which is really Q5. You can see here, third element. And because theta 6 equals theta 5 plus gamma, we had that in the constraint before. So now that we've got this position error, or we have all our vector loop scalar equations, we need to find the actual error values. So we will put this into a vector. Say error vector equals all of these different errors, xb, yb, xr, yr, xl, yl. Just put those all in a matrix and find the magnitude. Error equals norm of the error vector matrix. That norm value just squares up each element and then square roots them all to find the magnitude. So now to guess and check the answers, we will put in the Jacobian, update our guesses, determine the position error, and this will run while error is greater than the tolerance value. So looking here, this first big matrix, we'll have J times theta dot equals B. So J is that big matrix there, so we need to type that in. Now, because this is kind of a big, nasty looking thing to type, then we'll just go through one row at a time, and then we'll put them all together. So we'll say J of first row, vectors 1 to 6. So first row, columns 1 to 6 equals that first element, negative R3 times sine of, remember, Q3 is actually G of 1. And then the next element is R4 times sine of guess of 2. And then zeros, 0, 0, 0 to finish that out. That is the first row. So then we will type J of second row, columns 1 to 6, similarly. So now we have all the rows of the Jacobian. Then we need to update the guesses. So we have our old guess, and then we'll need to add the correction factor for the Jacobian and to get the new guess. So G equals the old G minus the correction factor, which is inverse Jacobian times the error matrix, error vec, which is also F. If you've watched my previous videos, sometimes error vector is the function matrix called F. So this I and V is underlined. You can see it says here it's slower and less accurate. So we'll use J backslash instead. Both ways work, but MATLAB likes the backslash a little bit better. Okay, so now that we have updated the guesses, then we need to, again, find the position error and see how close our guesses are. So we can actually just copy and paste all of this stuff here, and then we will just put it right down here. So that completes our while loop. So once the correct answers have been calculated, we need to save them. So we will fill in from the guess the correct spot of each of our arrays that we pre-allocated. So theta 3 of count equals G of 1. Theta 4 of count equals G of 2, and so on. Then for our constraint, remember Q6 of count equals G of 3, which was Q5, plus gamma. Now that we have finished with positions, let's figure out velocity. So in order to calculate velocity, we'll use the J theta equals B. So we have J, theta dot equals BV. So we need to find BV and multiply by inverse of J to get the theta dot matrix. So we'll define BV equals, and we have it in this column right here. So we need to put it in a column vector. So it will be R2 times sine of theta 2 of count times theta 2 dot, which we defined earlier. And then semicolon, because we're making this a comma vector, and just fill out the rest of it. So now that we've got BV, then we can say Q dot equals J backslash BV. And then we can extract all of the different velocity components from the Q dot to put in the arrays that we pre-allocated already. So Q3 dot of count equals Q dot of 1, and so on. So that completes the velocity. Now what we need to do is calculate the points to plot and then put those points into lines. So we'll need to define a point, or a point for every joint on here. So the easiest way to remember what all the points are is to go through and actually label them. I like to use a naming convention that is dependent on which two vectors are touching each other. So for example, this point right here would be P23 because R2 and R3 are connected. And then P34, P14, and so on like that. So P0 is just 0. Because that is the origin. Now, so that is the first point here. So then if we want this point over here, this is going to be P14, where R1 and R4 connect. And so we'll just connect that to the origin, P0x plus R1. Now, I could have just put plus 0 or not even plus anything. But if for some reason your loop starts at a place other than the origin, you would want to include that, like P0x and P0y would actually not be 0. So if for some reason your first ground point is not at the origin, you will have to add that on. So it's good practice. And that's why I did that for this example. So next we need, okay, so P23 is right here between R2 and R3. So P23x equals P0x plus R2 times cosine theta 2 of count. And P23y equals P0y plus R2 times sine Q2 of count. And then let's see. So then this point up here, we call that P34 because 3 and 4 meet. We call it P5, 6 because 5 and 6 meet. So it doesn't matter what we call it, but the next one we're going to do is this, whoops, that point right there. So now I'm just going to go on and fill in all of the rest of these. So we'll have P57, P68, P8, P9, and P10, P12, so on. I'm going to fill in all of those different points. So now that we've got all those points, we need to put the points into lines. So we'll want, we'll do the blue loop, the red loop, and the green loop all separately. So let's say XB for the blue loop is going to be, and notice that we used a capital X here. We use lowercases for the vector loop position scalars. So for the lines we're going to plot, we'll want to, these are matrices, we'll use capital letters. So you just want to make sure that you don't use exactly the same variable as you used somewhere else. So this line is going to go the blue loop. So we'll have P0, P23, P56, P14, and then back to the origin. So we'll put those all in. Or to close the loop, you have to put in the point where you started at. The red loop. So the red loop starts down here at P14, and then we'll have P56, P57, P7, P12, and then back to P14. So we'll put those all in. And finally, the green loop, or the left loop. So yeah, we call it either one, XL. For that, we're going to go from the origin. And then we'll have P23, P56, P68, P8, P9, and then back to the origin. Now that we've got these points into lines, we need to animate the plot. So to animate the plot, we'll start with making a figure. We'll just call it figure 1. And then we want to clear the figure from anything that was there before and then hold on. So it'll hold on to each loop. So we'll plot loops as lines. And we'll plot XL, YL in green. And we can make the line width a little bit bigger so we'll be able to see it. And then we'll plot the right loop in red. And then we'll plot the blue loop, or the bottom loop, in blue. We'll want to set the axis limits so that it won't distort and change size as the animation is running. So we'll say axis, and we need the X limits first. So we'll go from -1 to 10, and then the Y limits next. So we'll say -1 to 8, and then we'll see if that makes sense as it plots. So let's run this. We can see that no warnings are found. It's green. So let's run it and see if this works. All right, so it runs. Now you can see that we didn't really do the triangle. Oh, we only have 2 sides of it there. So the next thing we're going to do is put in the triangle. So for that, we want to use a patch command, and then we'll want to also color it in. The other thing we should do is add in joints. So we'll put dots at each of the revolute joints, and then we can actually make a square for the slider. So let's do some of that fancy animation stuff. So what we want to do here is first we need to define the vector of lines for the triangle. So we'll call it triangle X, and those points would be P56, P68, and P57. Now for the patch command, which makes a shape and fills it in, we don't need to connect the start back to the end because that does it automatically. So now we'll patch the triangle. So if we wanted the triangle just to be black, we can patch it like that. Then let's see, we also need to do the joints. So we need something with all of the revolute joints. So it doesn't really matter what order we put those in because we're not going to connect them as a line. We're just going to plot the joint points. So let's call it R for the revolute joint. So Rx equals P0x, P23x, P56x, P14x, and I should have started that with a bracket. So on just all of the X points that have revolute joints. And now we'll plot those joints. And we'll put the O in there to be the dot marker. Now we can fill in to make the inside of the dot white. We can say marker base color and white. So that will fill it in. That way we don't see the lines of the vector loop behind those dots. Then we need to do the slider, which the slider here is P8. So let's make that one a square. And we'll make it a little bit bigger. And we'll fill it in. Okay, so now let's run this and see what it does. But actually, let's check what is this warning or error that we have. Invalid syntax at close bracket. Oh, that, yeah, shouldn't have been a close bracket, should have been a parentheses. Okay, so we'll run this. All right, so that's good, except that we can't see the dot actually that's on the center of the slider. So we need to switch the positions of the slider and the revolute joints plot. And now we should be able to see that revolute joint show up on the center of the slider. Yes, there it is. Okay, so what if we wanted to make this a little bit fancier and have the triangle change colors? So for that, we would need to define a custom color vector. And basically we want it to use a different color depending on, like, each time it plots. So depending on, say, whatever the value of count is. So to do that, we will define custom color. Say we want this to flash in rainbow color, so we'll make our color called rainbow. And rainbow will actually be a matrix of all of the different colors. So red, yellow, green, cyan, blue, and magenta. So we have that. Now, that's only 6 colors, and our in value went all the way up to 20. So we need at least 20 of these. So let's see, 6 times 3 is 18, 6 times 4 is 24. So we would need at least this repeated 4 times in order for us to get through the whole cycle. So we'll make a new one called rainbow repeat. And that is just going to be rainbow, 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 rainbow. That equal sign in there. And then this is just going to repeat it so that as we go through this for loop, for each value of count, we're going to plot that patch as rainbows. So here we're going to put, for the color, which is the third element in patch, we'll put rainbow repeat parentheses count. So it will pull from one spot in there. All right, so here it is, flashing different colors for different color for each value of count. Okay. So what if we want it now to go back and forth? Because that, like, one cycle is not very long. So maybe we want it to wave from front to back. How are we going to do that? So for it to wave from front to back, we actually need to adjust the input. So if we're going, maybe we want to go back and forth 4 times. So let's change n, we'll say n equals 80, because we'll need more points. 20 seem good for one direction, but if we're going there and back, we'll do 80. So then we'll define theta 2. It's going to be that lens space, q start to q in. This time we'll do n over 4, because that would be 20. And then we'll stack 4 of these, and we'll say that Q2 equals Q2, and then we'll flip Q2. This flip command just flips it from front to back. So we go counterclockwise, then we'll go back clockwise, and then we can go again counterclockwise, and then go back clockwise. So that should make it go back and forth. But now remember, now that n is 80, we need to increase the size of our rainbow repeat vector. We'll actually probably need to put, we're going 4 more times. So let's copy and just paste this a bunch more times. So now we shouldn't run out of any colors. So here we go in one direction. And let's see, does it turn around and go back? When it gets to the end, yes, it does. So that went to the end and back, but it didn't go 4 times. So, okay, so what happened is we didn't divide n by 4, we only divided by 2, so that's why it only went back and forth. So 4 times, now we should get 4 different motions. You can see also that the square is not at an angle, but it's moving at an angle. There's no way to flip a square marker. You'd have to actually define 4 different points, and that just seemed like a hassle. Beautiful. So now the last thing we need to do is plot all of our points, all of our unknowns for positions, and then all of our unknowns for velocity. And let's make these 3 plots so it looks cooler, and we can see the series over time with the cyclic motion. So first thing we're going to do is define a time vector, t equals 1 to n, because of n points. So then we need to do position. And we'll make a position vector. And we'll just put in all of our unknowns into this position vector. So Q3, we'll put these side by side because they're column vectors. So then this will be sort of squarish. Q5, Q6, Q7, Q8, R10. Then make a new figure, figure 2. Hold on, and then we'll put a grid on. So, because it's 3D, it's easier to see with a grid. And then view 3. That will set the view to being 3 dimensions. Now to plot, plotting in 3D, the command is plot 3. So then we'll open parentheses, we'd need to do X, Y, Z, which, so on our X-axis, let's put time. On our Y-axis, we'll put the input, Q2. And on the Z-axis, we'll put all the unknowns. And because this unknowns is a big matrix, Matlab is going to plot each column in a different color. So that way we didn't have to type out for every single unknown. This is just a more efficient way to do that. Now X label is time in seconds. Y label is theta 2. So backslash THETA underscore 2. That is, we'll make a theta symbol. And then finally Z label will just be the positions. Some are in radians, some are in meters. So then legend. And title. Now let's just run this section. Oh no, we have an error. Let's see what's going on. Error. Okay, too many parentheses down there. Take that away. Okay, so let's run this section. And there's our plot of joint positions. So, okay, one of these is missing. A theta 4 didn't get typed out properly. Let's try that again. And we needed a backslash. So if you don't put the backslash, it just comes out as the actual word theta. You can see that there. Now this one is probably R10 based on how it just sort of floats out into space. But basically you can see the cyclic motion of all of these. So we have theta 2 here on the y-axis. So theta 2 goes up and down, all of the unknowns do. That makes sense. Time is on the x-axis here, and we are trending positively there. And then the z-axis is all of the unknowns. So all of the angles should be going, you know, up and down, up and down. Then it is a little weird how this R10 is just sort of constantly increasing. I'm not really sure what's up with that. So next, let's do the velocity. For velocity, we can copy and paste a lot of this. So we'll copy that, and then we'll paste here. And instead of position, of course, we'll call it velocity. And then we need all the Q dots. Our figure will be figure 3. We'll hold on, and then we'll plot velocity. We still want position because Q dot was a constant. We still want to show velocity versus input position because that'll show us a nice range. And then Z label will be velocities, and that will be radians per second and meters per second. So now formatting the legend is going to be a little bit different. So what we actually need to say is we need to give legend a handle, make it an object. So name equals legend. And then inside of here, we need to use latex formatting. So that will use dollar signs. Basically, to make the dots, we'll go $\dot, and then we need to open a curly bracket, theta underscore, actually theta, curly bracket, and then underscore, and put the 3 in curly brackets. Basically, every little unique thing has to be in a curly bracket, and then we'll end with the dollar sign. And then we need to do that for all of these variables in the legend. Okay, and so then we need to set the legend interpreter. So set name, interpreter, and then text. So then it knows how to interpret all of these symbols, and we'll call this joint velocities. And we'll run this section. So positions came through what unrecognized function or variable Q6 dot. Okay, so somehow we forgot to put in a Q6 dot. So let's go up to wherever we calculated velocity. Remember, Q6 dot and Q5 dot are going to be the same. So we'll just go over here and we'll say Q6 dot of count equals Q dot 3, because Q6 dot and Q5 dot are the same, since they are both connected on the triangle. Now it says Q6 dot appears to change size on every loop iteration. You know what? Doesn't really matter, because Q6 and Q5 dots are the same. We will just plot Q5 dot again. They'll be on top of each other anyway. So here are our velocities now. Again, this is cyclic, and they are a little spiky towards the end, and that's because the linkage is getting kind of close to a singularity. Let's see where it is right now. Okay, so this is not too much of a singularity configuration, but anyway, when the crank R2 starts to hit its limits, some of these joint velocities are going to try to shoot to infinity. So that's why you see these little spikes here. So anyway, this is our simulation, and it looks beautiful. There are lots of other types of cool things that you can learn to do in Matlab, but if you are trying to program an animation for a linkage that has multiple loops, this is a good way to start.